Okay, in this class we are going to discuss about advanced encryption standards. This is our YouTube channel DBS Talks. Please subscribe to this channel. Now let's get into our topic. Now let us see what is an advanced encryption standard. It is a more popular and widely adopted symmetric encryption algorithm which is likely to be encountered nowadays. Nowadays we are saying it as an advanced encryption algorithm. It is the most advanced encryption likely to be encountered nowadays, but we can say it as one of the encryption algorithm which is used to encrypt the data, but it is found at last 6 times faster than the triple of DBS. When compared with the data encryption standard, advanced encryption standard is 6 times advanced, at least 6 times faster than triple DBS. It is at least 6 times faster than triple DBS, and these are the features of the advanced encryption standards. The following are the features of the advanced encryption standards. First one is symmetric key or symmetric block cipher. It is going to give the permission to the symmetric. It is providing a symmetric key or a symmetric block cipher. It is the advanced encryption is performed on a 128-bit or 192 or 250-bit keys, and it is stronger and faster than triple DBS. Next one, it is a block cipher which operates on a block size of 128 bits. It is going to apply on a 128 bit of data, so we can say it as a block cipher for both encrypting as well as a decrypting. For both encryption and decryption, here we are going to use this. Here each and every round performing the same operations. That is, in each round we are going to perform the same operations, whatever the operations that we are going to perform in the previous operations, and at the same operation also it is going to perform here. Now let us see what is an AES. In 1990s, the cracking of a data encryption standard algorithm is became possible. If when you have applied on when you have applied data encryption standards on a particular data, then for a particular person who is going to attack on data, for that attacker, it is become easy to crack the data. So around 50 hours of brute forcing allowed attack. I think it is at most after 50 hours of brute forcing they can be allowed to crack that particular message. Then for this particular type of thing, some person need to do something. No, then NIST started searching for new feasible algorithm and proposed its requirement in 1999. So due to this drawback in DES algorithm, in the previous class we have discussed about NIST. NIST is searching for new feasible algorithms and proposed requirement in 1997. So in 2001, Rajendale algorithm designed by Richmond and the Demon of Belgium was declared as the winner of the competition. He is also declared as the winner of the competition. So in advanced encryption standard algorithm, we can say this one as a Rajendale algorithm. The person who is going to propose this algorithm here, and this is a specification for the encryption of electronic data, and is established by the US International Institute of Standards and Technology. AES based is a cipher. It is going to developed by the Belgian cryptographer. It is going to developed by some Belgian cryptographers, John Diamond and Vincent Richmond, who submitted a proposal to NIST during AES selection process. And here if it is a family of ciphers with different key and block sizes. For AES and NIST, they selected 3 members with which each block size of 128 bits, but 3 different key lengths of, but we have applied it in a 3 different key lengths, that is 128, 192 in 256 bits. And next one, it is also a symmetric algorithm. It is a block cipher. The size of a data block is 128 bits. we represent the data here. What are the things that we are going to apply on this particular block cipher? See, we can say it is not a asymmetric algorithm, it is a symmetric algorithm, and we can say it as a block cipher. Here the size of the data block is 128 bits. Here we represent the data block. How we are going to represent this data block is, here we are going to represent this data block by using a 4 by 4 matrix. It can also called as a state matrix. A state matrix size of each element in the, here the size of the each element in the matrix is 1 byte. Here the size of a key is 128, 192 and 256 bits. Here the key is expanded to the array of words. Here the each and every key is expanded here by using a array of words here. Now let us see how it is going to work. AES basically repeats 4 major functions to encrypt the data. It takes 128 bit block of data and key and gives a cipher text. It is going to give the cipher text as the output. For encryption, each round consists of the following steps. If you are going to do the encryption, it is going to, we have to perform the following steps there. First one is for encryption, each round consists of the following. First one is you have to substitute the bytes, that is you have to divide it into the sub bytes, and next you have to shift the rows, and next you have to mix the columns, and for that you have to add the round key. Next, for decryption, what you have to do is, first one you have to perform the inverse operation on substitute byte rows, and next you have to perform the inverse operation on shift row, and next you have to perform the inverse operation on the mixed columns, and for that you have to add the round key there. Next one, now let us see how it is going to work. Here the number of rounds performed by the algorithm strictly depends upon the size of the key. The following table gives the number of rounds performed with the input of varying key lengths. Suppose if it is of key 128 bits, then here we are going to perform 10 rounds. If it is of key 192 bits, then we are going to perform 12 rounds. If it is of key 256 bits, then we are going to perform 14 rounds there. Here larger the number of keys, the more secure will be the data, and the time taken by the software to encrypt it will increase with the number of rounds. Here the larger the number of keys, more secure the data will be. That is, if you are going to apply the larger number of keys on the particular data, then our data will be more secured, and the time taken by the software to encrypt will increase with the number of rounds here. See, here you are going to take the 128 bits of data here. Here you are going to perform the encryption on that particular data. Here M is a plain text with size 128 bits, and K is a key of size 128 bits, and N is, after performing the encryption, we will get the cipher text here. This is how we are going to perform the encryption, and see how the decryption is. For decryption, we are going to take the cipher text, and for that cipher text you are going to apply decryption on that. From that cipher text you will get the plain text. Here the term E refers to the encryption function for the symmetric block cipher, and the term M refers to the plain text message of 128 bits, and N is the cipher text, and K is the key of size 128 bits, which is same for both encryption and decryption, and D is equal to decryption function for the symmetric block cipher. See in this figure how we are going to convert the plain text into the cipher text. First you are going to take the 128 bit plain text, and next we are going to perform the pre-round transformation. Here we have performed that, we are going to perform so many rounds on that particular plain text. After performing so many rounds and adding multiple keys here, finally you will get the cipher text here. If it is of key size, based upon the key size itself we are going to perform the number of rounds. If it is of key size 128, we are going to perform 10 rounds here. If it is of key size 192, then we are going to perform 12 rounds here. If it is of key size 256, then we are going to perform 14 rounds here. See, this is a relationship between number of keys, number of rounds, and the cipher key size. See, here it is a cipher key. This is for decryption. This is a cipher key. We are going to add the round key for the plain text. We have, first of all, we have said we have to divide into the subbytes, then we have to shift into the rows, then you have to mix into the columns. After that you have to add the round key. This is process repeats until based upon the number of rounds you are going to perform. Based upon how many number of rounds they are going to perform there, based upon that number of, based upon the key size, we are going to perform the number of rounds. For that each and every round, this process is common. First of all, you have to perform the subbytes, then you have to shift the rows, then you have to mix the columns, then you have to add the round key there. This is the operation that is that we are going to perform here. We have already said, based upon the key size itself, we are going to perform the number of rounds. See, these are the steps for encryption, and these are the steps for decryption. For encryption, this is for an initial round, this is for a number of rounds, and this is the final round. This is for encryption. For encryption, we are going to take the 128-bit data block. Next, we are going to perform the key expansion. Next, we have next we have added the round key. Next we have to subbyte. We are going to perform the subbyte operation, and next we have a shift row operation, and next we perform mixed columns, and for that we have added the round key there. And here up to some final round we have performed this operation. Finally you will get the encrypted data block. Okay, now let us see for decryption how we are going to do here. For decryption, 128-bit encrypted data block we are going to consider. Next we are going to expand that particular key. For that you have to add the round key, and next you have to perform the inverse operation for the shift rows, and the inversion operation for the mixed columns for that in each and every round. Next finally you have to add the round key. From that you will get the 128-bit data block of a plain text. See how we are see what is the description of this algorithm here. First we are going to expand the key. The round keys are derived from the cipher key by using the Ejendale key schedule. AES requires a separate 128-bit round key for each round plus one more. And in the initial round, each byte of a state is combined with a block of the round key using the bitwise XOR. Using the bitwise XOR operation, each byte of state is combined with a block of a round key. Next one, for rounds, we are going to subbytes a linear substitution step, which each byte is replaced with another according to a lookup table. And next we have to perform the shift rows operation, a transition step where last 3 rows of the state are shifted, and cyclically a certain number of steps that we are going to perform there. Then we are going to perform the mix columns operation, a mixing operation which operates on the column on the state, combining the 4 bytes in each column. Then finally you are going to perform the round key operation. In that final round, no mixed columns, we are going to perform the sub keys, shift rows, and add round key operation there. See, these are the operations involved in the AES algorithm. First, this is the state, and next we are going to subbytes. After dividing into subbytes, this is the state. Next we are going to shift into the rows. Next we are going to mix into the columns. After that we are going to perform the round key. Here we have already discussed, based upon the key size we are going to perform the number of rounds. Here what we have to note down is, first of all, one add round key is applied before the first round. Before the first round itself, one round key is applied, and next one is third transformation is missing on the, here the third transformation is missing on the last round. See how we are going to expand a key here. In this key expansion process, here we the given 128-bit cipher key is stored in the 4x4 matrix. That is 16 into 4 by 4 means 16, that is 16 into 8, 128 bits. Then for 4 column words of this key matrix is expanded into schedule of 44 words, that is 44 into 4, that is 176. So the key schedule is responsible for expanding a short key into the larger key. these are used during the different iterations. Each key of size is expanded here, and 128 bit key is expanded to 176 bit key, and 192 bit key is expanded to an 208 bit key, and 256 bit key is expanded to 240 byte key. Here there is a relationship between the cipher key size, the number of rounds, and the expanded key size for an 128 bit key. There is one initial add round key operation, plus there are 10 rounds, and each round needs a new 16 byte key. Therefore we require 10 plus 1 rounds, that is 11 rounds of keys for 16 bytes, which equals to 176 bytes. Here the same logic can be applied to the two other cipher keys. The general formula that we are going to apply on it is expanded key size is equal to number of rounds plus 1 into block size. Here this is the first round, this is second round, and this is third round, and so on. Here based upon this we are going to divide it into number of words here. This is how we are going to perform the AES key scheduling. Suppose this is the AES key scheduling, and this is steps takes 128 bits, which key expands into array of 44 bit 32 bit words. Here this is the relationship between the cipher key and number of rounds that are expanded on the key size for a 128 bit key. Here we are going to perform the AES key scheduling here. This step takes 128 bits key and expands into the array of 44 to 32 bit words here. See, if the key received as input array of 4 rows and n columns, then nk is equal to either 4 or 6 or 8 parameters, which depends upon the key size. But the input key is expanded into array of 44, 52 and 60 words of 32 bits each there. Then see how we are going to divide these keys, that is k0, k1, k2, k3, k4, k5, k6 and so on, like that. For each and every this key is also divided into w0, w1 up to w40, that is up to 44 or 52 or 44 or 52 or 60 words of 32 bits each. That is up to 32 bits. We are going to divide it into the 44 bit or 52 bits, 42 bit key or 52 bit key or 60 bit key. Next one, this is how we are going to perform the encryption standard algorithm here. This one is plain text, and in this plain text we are going to divide it into you have to place it into the matrix of 4x4 matrix. After placing into the 4x4 matrix, you have to perform the initial transformation, and based upon the key that we have applied, if it is 128 bit key, then you have to perform 10 number of rounds. This is round 1, round 2, round 3 and so on, round n-1. Here up to round n you are going to perform, this is round n-1 and this is round n. Finally you will get some ciphertext, and the ciphertext is also placed in a matrix. For each and every transformation you are going to perform a round key operation. This is a key expansion here. Next one, this is the input state array and output. How we are going to take the input and how we are going to add the state array, and what is the resultant output that we are getting here. In the below figure, that is the key this is the expansion of key, that is how we are going to expand the key, that is in this figure. See, these are the advanced encryption AES operations that we are going to perform here. These are the sub-bytes operation, that is A00, A01, A02, A03, A10, A11. That is, this is rows and this is columns. This is A22 and this is B22. These are that is we are going to in sub-byte steps. Each byte in the state is replaced with the entry fixed 8-bit lookup table, that is S is equal to B S of B of I comma j here. And next one, this is a block implementation on the one state matrix. In one state matrix, here we are going to replace this one with this one, no? Then next you have to place S11 in this box, and next you have to take this S11 dash in this box. Then you have to take the S11 dash in this, and you are going to replace this here, and you have to take this S11 and you are going to replace this here. That is, by using this box we are going to replacing the state matrix, replacing the values in the state matrix. Next one, these are the subbytes table. How we are going to divide it into the subbytes, that is 0 0 0 1 0 to f, that is up to 0 to 15 we are going to divide. These are how we are going to divide it into the subbytes table. See, these are the inverse operation of the subbytes table. Here what it is in the row, it will be in the column here. What it is in the row, it will be in the it will be in the column here. That is the inverse of the subbyte table here. And this, see how we are going to transform this subbyte. These subbytes are, and the inverse subbyte transformations are the inverses of the each other. Inverse means you have already know how we are going to perform the inverse operation on the matrix. Suppose this is a 0 0 1 1 2 0 C and 0 8 at the 0 0 state. In place of here, in place of, see, if you observed, in place of 0 0, what is the 0 0, we are having the value 63 here. Just like that, simply by considering these tables, in 0 0 state we are having the value 63, and in 1 2 state we are having the value C9, in the 0 C state we are having the value FC. Just like that, we are going to simply we are going to transfer this matrix into transfer the matrix of subbyte into the inverse subbyte. So this is an example of the subbytes and inverse subbyte transformation. See, then how we are going to perform the shift row operation. In this operation, each row of state is cyclically shifted to the left depending upon the row index. The first row is shifted to 0 positions left, and the second row is shifted to the 1 position left, and the third row is shifted to 2 positions to the left, and the fourth row is shifted to the 3 positions to the left. The inverse of the shift row is same cyclically shift but to the right. It is needed later to the decoding. After performing the decoding operation, we can be do it later here. See how we are going to perform the shifting operation here. Here we are going to take one submatrix here. We are going, we are going to replace that S00 to S11, S11 to S02, just like that. We have seen already that table. By considering the table, we are going to replace these values here. See how we are going to shift the rows. See, by A10 to A11, A11 to A12, A12 to A13, A13 to A10. Just like that, simply we are going to perform the shift operation. See here, A00 to A01, A01 to A02, A02 to A03, A03 to A00. Just if we have applied the shift operation, how we are going to, in this first row there is no change, in this second row we have applied, in the third row also we have applied, just like this, from third to fourth, fourth to first to third, and third to row fourth, and second to third, and third to second. Just like that we have, and finally we have performed this shift operation. This is how we are going to perform the shift rows operation in this particular scheme. Next, what are the inverse of the shift rows here? Suppose if it is having F2 here, we are going to place this, we are going to replace this F2 here, and if you are having C9, then you have to replace this C. If you have to replace these two values here, and you have to shift these two values here. This is the shift row, and this is the inverse of the shift row. This is the state we are going to represent there. Then what is a mixed column operation? This is most important part of the algorithm. It causes the flip of bits to spread all over the block. In this step, the block is multiplied with a fixed number of matrices. For each row, there are 16 multiplication and 12 XOR and 4 byte output there here. This is how we are going to perform the mixed column operation in this particular AES standards. See, this is the example for the mixed column operation, that is S00. Suppose initially you are having some matrix and you are, first of all you have to take that one out and you have to mix that particular column to the resultant matrix here. This figure shows the mixed column operation, how we are going to perform here. See, this is a constant matrix, this is a mold matrix. Then what is the resultant matrix? We have to multiply 02 with 87, 03 with 60, 01 with 46 and 01 with A6. Just like that we are going to perform the multiplication. After that, what is the result we will get? We have to place that result here. Next that we have to multiply this row with this column, we are placing that result here. Next we are going to multiply this row with this column, we are simply we are placing the result here. So that these how we are going to perform the mixed columns operation in this advanced encryption standard is just like this. First of all, you have to multiply the constant matrix set to the with the old matrix, and next we are going to multiply the new matrix. This is the resultant matrix that we will get here. Next one, this is a mixed column scheme. You have to take this column here and you have to take this column, and next you have to take this column, and next you have to take that column, and next you have to multiply this column with the resultant matrix. This is the result that we will get with the resultant matrix that we will get. So we can say this one as a mixed column scheme. Then what is the add round key operation? In this operation, a round key is applied to a state by the simple bitwise XOR operation is performed here, and also the round key is derived from the cipher key by means of a key schedule, and the round key length is equal to the block key length, that is of 16 bytes. Suppose if a round key is generated, then the in the add round key step process, the subkey is combined with the state. For each round, a subkey is derived from the main key using the key schedule. Each key is as the same size as the state. The subkey is added by combining the each byte of the state with the corresponding byte of the subkey using the bitwise key or the bitwise XOR operation we are going to perform there. And next, in the add round key step, each byte of the state is combined with the byte of round subkey using the XOR operation. By using the XOR operation, here the in the add round key operation is performed, and the state is combined with the byte of round subkey by using the XOR operation we are going to perform here. Next, this is the add round key operation that we are going to perform. For each row, we are going to add the bits of words here. After performing the XOR operation, this is the resultant matrix that we will get. Next one, this is the RC4 algorithm. RC4 is designed by Ron Rivest, Adi Shamir and Leonard Adelman. These three people designed this RC4 algorithm. It is also a symmetric encryption algorithm. By using the stream cipher, it is going to design. It is a streamed cipher. Next, if you are going to perform the encryption, means that the pseudo random byte generator is there, it automatically generates a key, and by the cipher by receiving this cipher text, a pseudo random code byte generator, by using this, that key is decrypted and we will get this plain text. This is the block diagram of the RC4 algorithm. Next, this is the plain text, and after performing the RC algorithm, this is a ciphertext that we are going to get here. Next, this is the integrity check. We are going to perform the XOR operation, that is a shared key. We are taking this RC4 as the example. After performing the XOR operation, this is a ciphertext that we will get as a output. This is a stream byte, so we are for each and every time we are going to perform the XOR operation here. After performing the XOR operation, this is the resultant output that we will get. Then to convert this ciphertext, again you have to perform the XOR operation with some key stream. Then we will get the original plain text here. Basically RC4 is a stream cipher. This means for each bit, if plain text produces one bit of key stream and XORs, the two generate of the cipher text. The key stream is simply a stream of random numbers generated from the RC4 algorithm. In the most basic operation of the stream cipher, the algorithm is seeded with the key such that the same key will always produce the same stream of the random number. Since both the client and server know the key, they can produce the same key stream. This allows the client to the XOR to the plain text with the key stream to produce a ciphertext, and to the server to the XOR ciphertext with the key stream to produce the same plain text. This is about the RC4 algorithm. Then we will continue in the next class. Thank you.